Variational autoencoder. So basically this variational autoencoder is a type of neural network used for unsupervised learning, which means it can learn patterns and relations in data without being explicitly told what the desired output should be. Think of it like a puzzle where you have a bunch of puzzle pieces but you don't know how they fit together. So variational autoencoder will try to learn the rules that govern how the puzzle pieces will fit together so that it can reconstruct the original image from the puzzle pieces. So in the case of an image, this puzzle pieces might be an individual pixels and the image itself is a final puzzle. So this virtual autoencoder will learn a way to represent the image in a compressed form, which is called latent space, which captures the most important features of the image. And this compressed representation can be used to generate new images that are similar to the one that virtual autoencoders has seen before. For example, let us say you have a data set of handwritten digits from 0 to 9. Now this virtual autoencoder would learn to compress each image of handwritten digit into a smaller, more abstract representation in the latent space. It would then learn how to reconstruct the original image from its compressed representation, which will allow it to generate new handwritten digits that are similar to those in the dataset. So to summarize this, we can say that variational autoencoder is a neural network that compresses data into latent space and then reconstruct it from this, which will enable the generation of new data points that are similar to those in original data sets. So let's understand how it works. So basically this variational autoencoder works by training a neural network to learn a compressed abstract representation, which is a latent space of the input data, and then reconstruct the original input from this representation. So suppose you have a set of handwritten digits from 0 to 9. So here the variational autoencoder goal is to learn a compact representation of each digit that captures its essential features. So first encoder will process the image of handwritten digit through a series of layers, gradually compressing it to the smaller latent space. And during this process, virtual autoencoder will predict not only the compressed representation, but also the uncertainty associated with this. And this uncertainty allow the virtual autoencoder to generate new digits that are similar to those in training dataset. Then we have decoder. Now this decoder will take the abstract representation from encoder and transform it back to an image resembling the original handwritten digits. Then this virtual autoencoder is trained using a combination of two losses. First loss is scale divergence loss. Now the scale divergence loss encourages the predicted mean and standard deviation to be close to the expected value. The second loss, called reconstruction loss, will compare the reconstructed image to the original input, which ensure that the reconstructed image is as close as possible to the original. And during training, this virtual autoencoder will adjust its weight and biases to minimize the combined KL divergence and reconstruction losses, effectively learning a compressed representation of the data in the latent space, while also being able to reconstruct the original input. So in summary, we can say this virtual autoencoder will train a neural network to learn a compressed representation of data, which is called the latent space, and then reconstruct the original input from this representation. So this virtual autoencoder's ability to predict the uncertainty allow it to generate new data points that are similar to those in the original data set. So to understand this working, we have taken this examples where we will calculate this variational autoencoder by hand. So consider you are given a training examples which are fed into the network, and copy of those examples are used as target. So first here the autoencoder goal is to learn how to reconstruct the input data. Now this auto in the autoencoder refers to self reconstruction process. So first we have encoder, which has one layer 1, and then we are using the ReLU function. So in this, the input weight is multiplied with the weights and the biases here, and the ReLU will retain only positive values, which will allow the network to focus on important features. So here, if we consider the number of rows as 4, here the number of columns are 5, we will use the formula y is equals to wx plus p. So 1001 multiplied with 1231, adding 0 bias here, will get to here. So same way we'll multiply this 1001 with 1121, adding 0 here, will get 2 here, right? Now there is no negative term, so no value is used. Now in the next case, here the number of columns are 3, number of rows are 3, so 251 will be multiplied with 101, adding minus 3 here, will get 0, right? So here we will get the terms like this. Now whenever we have the negative value, we'll consider it as a 0, because ReLU allows only the positive values. So when we will have 002, it will be multiplied with 110, adding 0 here, we'll get 5. So similarly we'll get this thing. Now we have this encoder mean and the variance. So the input weight is multiplied by two set of weight and biases. The first set will predict the mean of latent distribution, right? And the second set will predict the standard deviation of this latent distribution. Now we have a reparameterization trick, that is we are using a random offset. So here sample epsilon, so E from the normal distribution with mean 0 and variance 1 is taken. The purpose is to randomly pick a offset away from mean. So we will multiply the standard deviation values with this epsilon values, and the purpose is to scale the offset by the standard deviation. Then we have the reparameterization trick, that is mean plus offset here. So here we will add the sampled offset to the predicted mean, right? And then results are new parameters or the features as input to the decoders. So here we are multiplying this mu plus sigma and doing this dot product with this one, right? So we are getting the matrix like this. Then we have decoder. So in this decoder, we will multiply this input weights with the weights and the biases, because here if we consider the number of rows as 2, number of columns as this one. So 10 multiplied with 15, adding 0 here, will get 1 here. Then you will apply ReLU, which that is key, you will cross out the negative values. So here minus 4 shall be considered 0. Then we have decoder layer 2. So here we will multiply the features with the weights and the biases. The output is decoder's attempt to reconstruct the original input from the reparameterized distribution described by mean and the standard deviation. And then we have this KL divergence losses. So where we have some loss gradients. In the loss gradient we want mu or the mean to approach 0. So lot of maths called SGVP simplifies the calculation of loss gradients to simplify this mu. Then we have loss gradients. So here we will use sigma minus 1 by sigma, right? So we'll get this 1 by sigma in this, and we'll get the terms. Then we have some reconstruction losses, that is we want the reconstructed data to be same as this input data. So here finally we'll get this output where involve the mean square error, that is y minus x. So we'll get the terms like this. So what are the applications of this variational autoencoders? So it can be used in the customer segmentation, that is variational autoencoder can analyze the customer behavior, preference and demographics to identify distinct groups or customers who share the common characteristic, and this information can be leveraged to tailor marketing campaign, product offering and promotions. Then it can be used in anomaly detection, so where it can learn a low dimensional representation of normal data behavior. So whenever a new data deviates from its learned representation, then it can be flagged as anomaly, indicating potential fraud, technical issues. Then it can be used in product recommendation. So by analyzing user interaction with the product catalog, it can learn the relations between the product and user, and this knowledge can be used to generate personalized product recommendation, improving user experience and driving sales. Then it can be used in image compression and generative modeling, where it can be used to compress images while preserving their essential features, reducing storage requirements and speeding up computations. Then it can be used in text generation, so where it can be used to sequential data such as text to learn a latent representation of input data, and this knowledge can be used to generate new text, for example product review, description or even news articles. Then it can be used in time series forecasting, so where it can analyze historical time series data, uncovering patterns and relations that can be used to predict future trends. And by accurately forecasting demand for raw material inventory levels, businesses can optimize their supply chain, reduce waste. Then also it can be used in the anomaly detection in the sensor data. So where it can be used to analyze sensor data from machinery and vehicles, identifying these unusual patterns that may indicate equipment failure or maintenance requirements. And in each of these examples, this variational autoencoder help business identify patterns and relations that might otherwise go unnoticed, allowing them to make informed decision, optimize their operation, and ultimately increase their competitiveness in the market. Thank you.